Okay, in the second part of this video, uh, I'm going to share once again the end of the lecture notes for what is planned to be completed this week. The main goal of this second video is how we can all the information that we went over in class, such as prepositions, statements that have a truth value, and we should be able to determine one for them. The truth value tables, how we connected them with logical operators, then how we took advantage of the logical equivalency laws, and then we applied them in different applications to show that two complex prepositions are equivalent to one another. In some scenarios, we were able to apply just one law, in some others, more than one to prove the equivalency. Now, we are going to look at the final topic of this week related what is known to a predicate. So for a predicate, I'm going to use an uppercase letter P. P comes from the word predicate. The idea is to look at prepositions now and the operators in the form of a function. And this is done if I use the argument of transitioning from uh, the arithmetic into the algebra, transitioning from numbers to variables, transitioning properties and operators used with numbers into using them with variables, and then transitioning into connecting two variables together, x and y, to build up that relation known as the famously known as a function, where each x is paired exactly with one y. So can we still use this argument, this idea for now for the prepositions and operators, logical operators and logical laws? So P of x is known as a predicate. If we look at this as a function, that of course as a function has an output. So you're thinking your sampling is entered as an input and then you're generating an output. So we look at the predicate P of x as a function that has an output that can be generate something true or false for each input of the variable. So if our common variable is x, I'm going to call this input x. So let's say that the predicate is x plus 1 equals 3. Remember when we had statements such as x plus 1 equals 3, we could not define them as prepositions unless some value of x is plugged in to change this into a preposition and then allow us to determine the truth value. It's that particular idea. So if I select x to be 1, the other thing later on we'll see that there's a domain, a space that allows us to select the values of x that are going to once again allow us to determine the truth value of this predicate. Let's pick x equals 1. If I choose x to be 1, then this statement x plus 1 equals 3 now becomes 1 plus 1, which we know is not 3. So automatically the input value 1 changes the predicate P of 1, now becomes a preposition that has a truth value of false. And then if I select x to be 2, then P of 2 is true. So that's the whole idea behind it. And then we'll definitely transition into more than one variable scenario. We'll do this verbally with some statements to allow you to understand this. The other thing that we'll do is we'll define some quantifiers. So, what are the two major quantifiers? One of them is known as the existential quantifier. Existential, the word starts with an E. This is, by the way, this is uh, a letter that is popular in the Greek alphabet and then is translated into there exists an X. And then we do have the universal quantifier. This is the notation of it. The notation that you see looks like an upside down A, uppercase A. So the universal quantifier translate into for all x. So let's look at some statements. So if I say the existential quantifier x p of x. How do I read this? So we read this as there exists a value of the input x, at least one x, such that p of x is true. Now let's transition into the verbal statement of the universal quantifier, which is for all x, p of x. How do I translate this? P of x is true for all values of the input x, or every possible x. So now let's go back and revisit the same example. Remember, we have the statement x plus 1 equals 3. Let me define a domain where I'm selecting my x's. So this is the space. The space is all, let's say, all integers, not real numbers. So I have p of x, the predicate, to be x plus 1 equals 3 for all x's in the set of integers z. Let q of x be the input x is the day of the week that ends with letter y. So now notice now that I'm proceeding with two predicates. So I have a p of x and the q of x, and they're two different input. One is based on the domain days of the week, the other one the domain set of all integers, based on how the statements are defined. So we are going to look at this and then determine the truth value using quantifiers. So first, existential quantifier. There exists an x, input x, such as p of x. There exists an integer x that makes the statement x plus 1 equals 3 that is true, x equals 2. This is which is x equals 2. Now, for all x, p of x is false. And this is indeed a statement that can be translated into let the value of x be all integers different from 2. So if I pick all integers different from 2, then p of x is false. Now let's try to transition into the other statement. So since we did spend a lot of time understanding the first one, it's more like a mathematical design. Now let's look at like a typical verbal statement, how this is going to apply to a typical verbal statement. Remember, the q of x is a day of the week that ends with the letter y. So what is the existential x q of x? Is true. There exists a day of the week, such as Monday, that ends with the letter y. And then the universal quantifier for all x, q of x, is true. Y for all x, q of x is true in the domain days of the week. If you look at every single day of the week, they're all ending in y. So we can say all days of the week end with y. So no matter what x is that you're selecting in the domain days of the week, the statement is going to be true. So different from the previous one, looking at the domain, you may end up with predicates that are going to be always true, no matter what you're selecting. And this goes back to tautologies and contradiction. Remember, tautologies are prepositions that are always true. Now, I'm going to skip this example. Notes are in there. I'll let you study, and then I'm going to transition into negating quantifiers. Remember, we have an existential quantifier that exists an x p of x, and then universal quantifier for all x p of x. How do we negate them? If I negate them, you notice the negation sign, then the existential notation becomes for all. So from the words verbally there exists an x, now if you negate it becomes for all x. For all x, it's not going to be a p of x. You're negating p of x as well. So if I negate the statement existential x p of x, that becomes for all x, not p of x. And then for the same reason, if I negate for all x p of x, this becomes equivalent to there exists an x, not p of x. And then I'll let you look at this nice example and then including the negation part of it. And then I'll transition finally into an example that is including, there are two good examples for you to see with one single variable. but there's no reason for us to think that predicates are functions of a single variable. As you have seen it with other examples, two variables can be involved. So let's f of x be the predicate that x is your friend. And now I'm going to define f of x and y, so two variables, which means x is friend with y. So what are possible how do we quantify this predicate? Remember, I have two variables. So the existential and then the universal are going to be for the two variables. So let's take a look at the first one. There are possible ways to quantify this predicate. So for all x and for all y, f of xy, which means everyone is friend with everyone. Remember what f of xy is? X is friend with y. So for every x, for every y, f of xy, which means everyone is friend with everyone. Now, for every x, so I'm taking all x's, there exists y. So for each x, I will be able to find a friend y. So everyone is friends with someone. So for each x, I will be able to find a y. Now, there exists an x for all y. That means someone is the friend with everyone. And then we'll end up with there exists an x, there exists an y, f of xy, which means someone is friend with someone. So this is like more likely one-to-one scenario. And then if I have to negate this, I will do one and I'll let you do the other ones. Remember what my first one is for all x, for all y's, for all y, f of xy, which means everyone is friend with everyone. How do I negate this? For all x becomes there exists an x. For all y becomes there exists y, not f of xy. So not p, but f of xy. And then you feel free to look at the other one. So more when you're negating for all, so when you're negating the very first one, this more likely becomes very similar to the last statement. So this is for all x, for all y, f of xy, negated becomes there exists an x, there exists a y, not f of x and y. So you'll be able to find an x friend and then y that are not going to be friends with one another. So someone is not friend with someone. If you look at the last statement, for all becomes there exist. For all x, there exists an x. For all y becomes there exists a y. Now, all x is everyone is friend with everyone, but we are negating f of xy. So for all x becomes there exists an x. For all y becomes there exists a y. And now we are going to say not someone is friend with someone, but someone is not friend with someone. So there exists an x that is not friend with, there exists y, such as someone is not friend with someone. And this is where I'm going to stop. And then I will be posting the solutions of the study guide as well. And then if a short video explaining the study guide I think will be beneficial, I will record it and then do the same thing. So once I record